So let us start our lecture today. So last time we was trying to solve the following equation. We have x squared uxx plus x ux plus lambda u is 0 on x belongs to 1, and you want to have Differential boundary condition at 1 and at 8. So this is the SMUMATH Eigenvalue Problem. Right. This is the problem that we were considering during last time. We have x squared plus the second derivative of u plus x times the first derivative of u plus lambda u is equal to 0 on the interval 1a. We have two boundary conditions. The first directional boundary condition at 1 is 0, and the second directional boundary condition at a is 0. This is a SMUMATH problem, eigenvalue problem, and we have to solve this equation, right? The first step is to find w. Find w. We need to find the w such that you have a separate choice operator, right? So again, this operator will be the operator. Will be Lu is x squared plus uxx plus x ux. This is the operator. Lambda is the eigenvalue and u is solution, right? So in this case, the operator is just this part. This is the operator. Now, what we have to find is the w, right? We need to find w to define the inner product fg is equal to the interval from 0 to a wx fx gx dx, all right, such that L is self-adjoint with this inner product, right? So we need to find the w such that you have L u v dx is equal to integral from 0 to a of wx.
Does the interval not go from 1 to a?
Is it? Yes, from 1 to a, thank you. So this is from 1 to a. V dx. Alright, in which v will satisfy the same thing, right? So you're gonna have LV is x squared uxx plus x vxx plus vx with the same boundary condition. U va at 1 is 0 and v at a will also be 0. Right, so can you sign at the back of the paper, please? All right, so let me explain this again. You have this equation. The operator will be the part that doesn't contain lambda, right? The operator will be the part not containing lambda, right? So lambda is the eigenvalue. So the operator will be the part depending on u, right? So the operator will be the term that depends on u, and that term doesn't contain lambda, right? So the operator will be x squared plus times uxx plus x ux. Now, we want to find the weight w such that the weighted inner product fg weighted w, which is the interval from 0 to a, wx, fx, gx, dx, this inner product will make the operator L auto-choid or self-choid. In other words, if you consider LV that satisfies x squared vxx plus x vx with the same boundary conditions, then you're going to have the interval from 1 to a of wx L u v dx will be equal to the interval from 1 to a of wx L v u dx. Right? Now, what we have is the following. So you're going to have Lu is going to be 1 over w. Right? You're going to find the weight w such that you have wx squared uxx plus wx ux. Right? So I can write the Lu as 1 over w, wx squared uxx wx ux. Right? It is the same because you multiply by w and then you divide by w. So it's going to give you the same with this guy. Right? So this is going to give you x squared uxx plus x ux. Right? So the weight w, so we follow the previous method. We're going to need a w weight. Here we're going to divide by w, and here I'm going to have w, I'm going to have to multiply by w, right? And we're going to need, we will need w x squared prime is equal to wx. This is how we choose w, right? If we have this guy, if we have this relation, what we're going to have is Lu will be 1 over w, wx squared uxx, u second, plus wx squared u prime, and this is going to give you 1 over w, wx squared u prime. The explanation is the following. So you have wx squared u prime plus wx squared prime u prime will be wx squared u prime. Now explain again. How do you choose w? You follow the previous method. You're going to have to multiply w here, and you're going to divide w here. This is just a different way of expressing x squared uxx plus x ux. Right? The trick will be, you're going to choose w such that wx squared is equal to wx. When you have a wx squared is equal to wx, you're going to have Lu is 1 over w, wx squared u second plus wx squared prime. Because here you already have wx will be wx squared prime, right? Because if you have this relation, if you have wx squared prime is wx, you're gonna replace that the wx by wx squared prime. Now, because you have wx squared prime here, I'm gonna have wx squared u second plus wx squared prime u prime. This can be written like wx squared u prime prime. Right, so this is a product rule. So you have wx squared u prime prime will be wx squared u prime prime plus derivative of this one times u prime. So you have wx squared prime u prime. Questions? Now I'm gonna record you what we did in the previous times. So in the previous time you have what? You have u second plus 2u prime, right? So this is what we have in the previous class. You have what? You have the LU will be u second plus 2. It's better, right? So in the previous class, we consider this example. LU will be u second plus 2u prime. All right? So this is written like W, 1 over W u second plus 2u prime. Right? Here, they want to, we replace 2 such that here you have W. Right. So I explain again. In the previous class, you have u second plus 2u prime. What we did is that you divide everything by W and you multiply everything with W. We choose 2W to be equal to W prime. Alright? Here, then you get 1 over W second, plus W prime, U prime. Right? And this gives you 1 over W prime, U prime, prime. This is what we did in the previous class. So in this class, in this case, you do the same. You divide both sides, you divide the operator by W and you multiply by W. And you want the coefficient of U second prime to be the coefficient of U prime, right? Which means that you're gonna have Wi squared prime is equal to this coefficient of Wx, right? When you have that one, you can convert this operator into the form of Wx squared U prime prime. Because you have the product rule, Wx squared U prime prime plus Wx squared prime U prime will be Wx squared U prime prime. Questions? It's clear? Right, so this is how you choose it. Now let us try to find W. In order to be able to find W, you have to know how to solve first order differential equation. Right? So now we find W such that Wx squared such that Wx squared prime is equal to Wx. Alright? Which is this equation over here, right? So you have to find W such that Wx squared prime is equal to Wx. Now I'm gonna do, so how do we solve this equation? How do we find this W such that, yes?
The W includes the term of x.
Yes. So
because derivative derivative of W times derivative of x squared.
So first you have to take the derivative of this guy, right? Can you say at the back of the paper, please? So you take the derivative of this guy. So you have Wx squared prime will be W prime times x squared plus x squared prime times W, right? Now this gives me w prime x squared plus 2x w. So now you're going to have wx squared plus 2x times w is wx. Right? It's clear? The first thing that you have to do is to do the derivative from the left hand side because it still have w and x squared. You do the product rule, you have wx squared prime will give you w prime x squared times x squared prime w. Right? So this is w prime x squared plus 2x w. You're going to have w prime x squared plus 2xw is wx. Alright? Now, here you have 2 times wx and here you have wx. So now you have w prime x squared plus x times w is 0. Now how can we solve this equation?
Eigenvalue problem?
No, this is not eigenvalue problem. This is first order differential equation, right? This is first order differential equation. How did you solve it? We know it from the previous class. So what is the trick? No.
Characteristic equation?
Right? Sorry?
Characteristic equation?
No, it's not characteristic. You have x w prime x squared plus xw is 0. How do you solve this first order differential equation? This is first order differential equation. No.
Yeah, you don't separate?
Yes. So you're gonna separate x and w. Right. So who is you said that? Can you say at the back of the paper, please? So you're gonna separate x and w, right? So you're gonna have w prime x squared is minus xw. You're gonna put w to the left hand side and x to the other side. Now this is w prime over w is minus x over x squared, and this is 1 minus 1 over x. Alright? So you're gonna group w to one side and x to the other side. This is called a method of separable. So this equation is separable, and the method is separating variables. Right. So this is in chapter 1 of Haberman, which is the one that I posted online. So this is the very first lecture in differential equation. All right. So I explain again. You want to find w such that wx squared is wx. All right. So wx squared prime will be w prime x squared plus x squared prime w. And x squared prime will be 2x. Right. So you have w prime x squared plus 2x w. You replace it to the left hand side, you're going to have w prime x squared plus 2x w is wx. You remove one wx on both sides, you have w prime x squared plus xw is 0. This equation is a separable equation, right? So this equation is separable equation. This is called a separable equation. Which is the very first differential equation that you learn how to solve. Again, to remind this is in differential equation class 3133. So I posted chapter 1 of Haberman book. So to solve a separable equation, you just have to separate x and w, right? So you put all of the x to the other side and all of the w to one side. And now you have w prime over w is minus 1 over x, right? So from here, how do you solve it?
You integrate?
You integrate, yes. Can you sign the back of the paper, please? So this is something that we encountered in the previous class, right? This is something that we know in the previous class. We have w prime over w is is log of W prime. So this is what we learned from the previous class. We know that W prime over W is log of W prime, right? Which is again log prime of W times W prime, and this is W prime over W. This is chain rule. Right? So you have log of W prime is minus 1 over x. To find this, you just have to take the antiderivative. So log of W will be the antiderivative of 1 over x dx, and this is minus log of x plus some constant, but here we don't have a constant, right? Right? Right, so did I make some mistakes somewhere? Is minus 1 over x. Yes, no, it's fine. Right, so to find W, then you have to take the W will be exponential of log W, right? And this is exponential of minus log of x. So this is 1 over exponential of log of x. And this is 1 over x. So you know that W is 1 over x, right? So I explain again. Here you have to find a weight. To find a weight, you have to have Wx squared prime is equal to Wx. This is first order differential equation, and this equation is separable. Because when you take the derivative of Wx squared, you're gonna get Wx squared plus x squared prime times W. And this gives you W prime x squared, and x squared prime will be 2x, right? Then you're going to have W prime x squared plus 2x W is Wx. You remove Wx on both sides, you have W prime x squared plus Wx is 0. This is separable because you can put all of the x into one side and all of the W to the other side, right? So this is so the W is on one side and x is on the other side. Right? So this is separable because you can separate x and W. You're going to have W prime over W is minus x over x squared, right? And this gives you minus 1 over x. So to solve this is easy. So we in the previous class we know that W prime over W will be log of W prime, right? So you're going to have log of W prime is minus 1 over x, which means that log of W is the antiderivative of minus 1 over x. This gives you minus log of x. You solve it and you get W is 1 over x. Yes?
Why do you, so like ln of W equals negative ln of x, and then you exponentiate both sides, why is it 1 over x instead of W equals negative x?
W is negative x. Good question. So yeah, so if you have log A
Like you put W
is minus log B, and A is not minus B. Because log is taken only when A and B are negative, are positive, right? So if A is minus B, meaning that B is minus B is negative, so A cannot be minus B, right? So A is minus log of B means that A is 1 over B, right? So log of A is minus log of B means that A is 1 over B. Right? It's clear. Right, so it's like log of E is 1 and log of 1 over E is minus 1. Right? So what is log? Log is the power. So I recall you that what is log? Log is the power. So log of x is n, meaning that e to the n is equal to x. So log is this power, right? Log is this power. So log of x is n, meaning that this power is n, right? So 1 over x will have will be e to power minus n, right? So which means the log of 1 over x is minus n, right? So log is the power. Other questions? It's clear? Now, let us go back to our problem. So we have what? We have log of u is what? Log of u is x squared u second. Log of u x squared u second plus x u prime. Right? So what we do is trying to write this as 1 over wx squared times u prime plus wx u prime. And I'm gonna set this to be wx squared. So I'm gonna have 1 over wx squared times u second plus prime wx squared prime u prime, right? And this is 1 over wx squared u prime prime. This is what we get at the end of the day, right? So the goal of everything is to get rid of the term here, so that you have only one term like this. And w is chosen such that wx is equal to wx squared prime, and we have w is 1 over x. And I'm gonna show that this operator is self-adjoint, right? To convince you that this is good. So L is self-adjoint. Is self-adjoint. Meaning that you're gonna have interval from 1 to a of w lu v dx is equal to interval from 1 to a of w lv u dx. Now I want to convince you that this operator is self-adjoint, meaning that I have w times lu, v is u times w times u lv. LVU, right? Yes. So I'm gonna show you that this operator is self-adjoint under that weight, right? So I'm gonna have W LUV is equal to W LVU, right? So from that expression, I'm gonna have MU will be 1 over W W x squared U prime. I'm gonna replace this to the left hand side. So the left hand side will be integral from 0 to a w 1 over w wx squared u prime v dx. All right. So by choosing that w satisfy this relation, I'm gonna have mu will be 1 over w x squared u prime. So I replace that relation here. I'm gonna have this one. So this gives me 1a w x squared prime v dx. Questions? Right. So I'm gonna remove w and that 1 over w. Right. Right. So now, how do I continue? Integration by part. Can you sign the back of the paper, please? So now you do integration by part, and this gives you wx squared u prime v the difference from 1 to a minus integral from 1 to a w x squared u prime v prime dx. This guy is 0 because v at 1 and a, they're both 0, right? So this guy is 0. So I'm going to have w a squared u prime a v a minus w1 1 square u prime 1 v1 minus the interval from 0 1 to a wx square u prime v prime dx. Alright, so this is 0. This is 0. So this gives u interval from 1 to a wx square u prime v prime dx. Right? And similarly, by the same argument, you can check. You're gonna have the right hand side will also be the same thing. So which means that the left hand side is equal to the right hand side. So the operator is self-adjoint. It's clear? Questions? Right. So here the key idea is to find w is to write. To find the key idea here is the following. The key idea here is to write w like x squared u second plus x u prime, right? And then you're gonna have 1 over w wx squared u second plus wx u prime, and you set wx squared prime to be wx. This is basically the key idea to get us, and then L is self-adjoint. In the inner product with yw, right? So this is the key. No matter what I said, this is what you need to remember. This is the only thing that you remember. You write x squared u second plus x u prime. You put 1 over w here, you put w here, and you're gonna set this prime is equal to this one, right? This is the key idea. And if you do that, L is self-adjoint with respect to this w. I'm going to show you some other cases so that you understand how to use this idea. So example 1. So you have sinus of x u second plus x u prime, right? So you have this operator, right? So how do you find w? It's going to be the same. You're going to write Lu is w 1 over w sinus of x u second plus w x u prime, and you're going to set w sinus x prime is equal to wx. Alright? This is the w that you are finding. So the key idea is what? This is the operator, right? You multiply w to both sides. You multiply w here and here. Of course, you have to divide by w. Alright? Now after multiplying, you just set this derivative is equal to this one. So you're gonna set w sinus x prime is equal to wx. Alright? So how do I solve this equation? Separable. I solve this by separable, right? So this one is w prime sinus of x plus sinus of x prime times w is equal to wx. Alright? So you're going to have w prime sinus of x plus cosinus of x times w is w x. Alright, so I'm going to have w prime sinus of x is equal to wx minus cosinus of x. W over w is x minus cosinus of x divided by sinus of x. Right, so this is separable. Separable. Right, so then you can have wx prime is x minus cosinus of x over sinus x. Right, so w will be e to the antiderivative x minus cosinus of x over sinus x dx. Right, so you use the same method that we discussed before. So I explain again. This is another example where where you can use the same method to find w. Right, so you have sinus x u second plus x u prime. All right. You're going to try to find w. So to find w, you divide by w and you multiply with w. Then you're going to have w sinus of x u second plus wx u prime. All right? So you're going to set the derivative of this guy is equal to this guy. So you have w sinus of x prime is equal to wx. The derivative of this guy is w prime sinus of x. This is sinus of x prime w. So sinus of x prime is cosinus of x. So now you have w prime sinus of x cosinus of x, w is wx, right? You want to group w prime sinus of x is w, x minus cosinus of x. Now you do separable, right? So you have w prime over w is x minus cosinus of x divided by x. So the leftover is, the task now is to do the antiderivative of this guy. Alright? So far so good. Questions? It's clear? Right. So another example is this one. Now you have one example number 2. Mu is x square u prime plus x cube u prime. All right. So this is another kind of operator. So this is mu is x squared u second plus x cube u prime. All right. So you have w is 1 over w wx square u prime plus x cube w u prime. So the first thing to do is to multiply by w and divide by w. Right? And the next thing is to set w, x square prime is x cube w. Right? So you have w x square prime is x cube w. So this gives you x w prime x square plus 2x w is x cube w. Right? So w prime x square is x cube minus 2x w. So w prime over w is x cube minus 2x over x squared. So this is x minus 2 over x, right? And you continue like in the previous case. So I explain again. Another case, another example is Lu is equal to x squared u second plus x cubed u prime, right? So to find w, you're going to divide by w and you're going to multiply by w. Then you're going to have wx squared prime, which is this one, prime is equal to this one, right? So you have wx squared prime is x cubed w, which give you w prime x squared plus 2xw is equal to x cubed w. Now you do separable. You have w prime x squared is equal to x cubed minus 2xw, you divide by w, you divide by x squared. This gives you x minus 2 over x. So w prime over w is x minus 2 over x, and you continue like this. Right? Questions? Right. So in all of those cases, I don't put any coefficient here, right? So what happens if I have x squared u? This is what you asked last time, right? So let us go to that case. Right, so we go back to this example. You have Lu is x squared u second plus x of u prime, and the condition at 0 and at a at 1 and at a will be 0. Right? Now, so what is the w that we choose? Any idea? Y 1 over x minus 1 over x, like in the previous one. You just don't care.
Say y.
No, sorry. Suppose that I have x in u, right? So what is the w for this? What is the w in this case?
With x squared, you need x squared w prime may equal x plus x w.
So in this case, it's much more complicated. It has this x u, right? So, but I want to a w such that this is auto-adjoint, self-adjoint, right? What is this w? You can tell in one shot. What is this w? U1 w Lu v 1 to a dx is equal to 1 to a w lv u dx. Right? So you know the w for the operator without xu. What is the w for the operator with xu? It's going to be the same. You don't care about this linear zero order term, right? So the w will be minus 1 over x. It's going to be the same in the case you don't have xu. The reason is the following. Right? So I'm gonna write Lu to be 1 over w x squared u prime prime plus w x prime plus w x u. Right? And I'm gonna set w x squared prime to be wx. Right? So this operator will give me 1 over wx squared u prime plus 1 over w plus wxu. All right? All right? So I still choose w such that wx squared prime is wx. In this case, you have this guy, which doesn't seem to be nice, right? But I still can claim that this is satisfying. Why is it? So when you have the interval from 1 to a at w l u v, I'm gonna have this is 1 over a w times 1 over w wx squared a u prime plus wxu. Right? So I'm gonna show you that with this way. the operator is still self-adjoint, right? So I'm gonna do the same thing with before, except that I have this new term. All right? Now, I'm gonna multiply W with LU. So this W will go away with 1 over W. So you're gonna have 1 over A W x squared U prime, and I have V here, right? V plus x U V. Vx. Right? Yes?
Should there be a W on that last term also?
Yes. Nice and so W. Thank you. Can you sign the back of the paper? Right? So I'm gonna do the same thing, except that in this case you have this guy, which is there, right? So in the previous proof, what we did is to do integration by part, right? So the first term will give me 1 minus 1 over A W x prime U V prime dx plus integral from 1 to A W x U V dx. All right. So this is integration by part. So this is something that we did in the previous time, right? So this guy give you this one guy, right? So this guy is still there, right? From the previous computation, you know that this one will give you 1 over A W x squared V prime U dx. Right? So this one is giving you this. And the other one is this one. W x U V dx. Alright? So because from this line to this line I use integration by part like in the previous one. Right? But here I don't have any derivative, so I still keep it. Alright? But from the previous step, I know that this is also equal to this one, in which you change from U to V, right? So this is nothing but the operator W x squared V prime 1 over W. All right. I missed something? Yes. This is nothing but integral from 1 to A W 1 over W W x squared V prime U plus W V U dx. Alright, and this is 1 over A W LV U. Yes. So the self-adjoint only concerns the derivative, right? So because here you have something that doesn't concern the derivative, so it will propagate to the end, and the operator is still self-adjoint, right? So in the case that you have this term, you don't care about that. You just choose the W for this operator, and the operator is still self-adjoint. Right? Questions? Right. So I think I have 2 minutes, so I'm gonna try to explain to you the eigenvalue problem. And this is
on
important.
that integration by parts, did you not include the first term because it won't zero out?
This one?
Yeah.
This one?
On the top line, the integration by parts did not include the first term because it zeroes out.
So you have this term and this term, right?
Yeah, but like the integration by parts is like A dB, right? Or AB minus integral B dx.
It's zero.
This
It's zero.
Zero.
This is zero, right? So from here to here, this is the computation that we did in the previous minutes, right? So from here to here, you do integration by part. There's a boundary term which is 0. Here you don't do integration by part, and this is the good thing. This is why you add this guy there, and this is still the same until the end. This is why the operator is still self-adjoint, right? All right, so I got in the on Wednesday, I'm gonna try to solve the eigenvalue problem. I mean, to find the eigenvalues and the eigen functions, and this will be in the exam explicitly.